what we need to consider when dealing with different atomic isotopes is we need to deal with their abundances. So if we have copper, which is 69.17% copper 63 that has a mass of 62.9396 AMUs, and the rest of it is copper 65, which has a mass of 64.9278 AMUs, using these percentages and these masses, we should be able to calculate copper's atomic mass. All right, so we need to look at what we're given. So we're given that copper 63 is 69.17%, and we're given its atomic mass in AMUs. And we know that the rest of it is copper 65. Well, how are we going to calculate its abundance? Well, we'd take 100 minus 69.17%, and we know its atomic mass. So what are we trying to find? We're trying to find the average atomic mass in AMUs. So our conceptual plan, well, we're going to take isotope masses and their isotope fractions, and we're going to combine that in a way to get our average atomic mass. So what's the relationship? Well, for the relationship, to calculate atomic mass, we're going to have to take the sum of the fractional abundance of the isotope times the mass of the isotope. Now, that sounds more complicated than it actually is. Now, first, that symbol there, if you don't recognize it, looks like a Greek E. That means the sum of. So what does that mean? Well, we're going to look at that in the next step. Right? So we have this relationship. So let's look at using that relationship to do our calculation. So first, we have to get a fractional abundance of the isotope. Well, if we know we have a percent abundance, the fractional abundance is just taking that percent divided by 100 to give us a fraction. So for copper 63, its fractional abundance is 0.6917. For copper 65, we ended up with 30.83%. Remember that 100% minus the 69.17. And so its fractional abundance is going to be 0.3083. So in order to do this calculation, we have to take the fractional abundance times its atomic mass, and we have to do that for both the copper 63 and the copper 65, and then we add those values together. So for the copper 63, we'd get a mass of 43.5353 AMUs. For the copper 65, we get the 20.0172 AMUs. All right, now, to avoid rounding error, we're going to use those values as is, even though each one of them should only end up with 4 significant figures. We need to keep that in mind, because if each one ended up with 4 significant figures, it'd end up with 2 decimal places. All right, so when we add them together, we'd get 63.5525, and then we'd consider at the end rounding to the 2 decimal places. So really our correct answer would be 63.55. Okay, so always remember those significant figure rules when dealing with these kind of combined calculations. But also remember, try to avoid that rounding error. Right, so we end up with the 63.55 AMUs. Now to check it, if we look at the relative masses and we look at their abundances, we know roughly 70% of copper occurs naturally as copper 63. We know roughly 30% occurs as copper 65. So when we look at our overall atomic mass, our average atomic mass, it should be closer to the 63 than it is to the 65, because a larger percentage is going to exist as 63, and it does. Right, now, this seems like it may be a little bit complicated. It's really not that bad, and you need to practice some of these. Right, so let's look at another example of this. So we have gallium-69 with its mass, and we have gallium-71 in its mass. And we actually have the average mass of gallium. What we want to do is calculate the percent abundance of each isotope. So keep in mind this equation. When we go to our solution, if we look at gallium-69, we don't know what its percent abundance is, but we do know if we call that X percent, we do know we'd take X divided by 100. Well, 1X divided by 100 gives us 0.01X. We know that gallium-71, its percent abundance would be 100 minus the percent abundance of the gallium-69, and to get its fraction, we'd then divide by 100. So for the gallium-71, it would be 1 minus 0.01X. Okay, and keep in mind, we're trying to solve for X. And all we're doing is using that equation in blue there, and we're just substituting in different things into that equation. So now, we know that the atomic mass is 69.72. We know the fractional abundance of gallium-69 is 0.01X. Take that times its mass. We know the fractional abundance of gallium-71 is 1 minus 0.01X. Multiply that by the atomic mass of gallium-71. When we calculate that out, we get these values. Now we need to combine our x's and then combine the values that don't have x's associated with them. Basically get all the x's on one side and all the other values on the other. And when we run through that calculation, we end up with x being 60.26. That's going to be our gallium-69 abundance. And then we just take 100% minus the 60.26%, and that's 39.74%, which is gallium-71 abundance. Now to check this, well, if we look at the average mass is 69.72. Is that closer to 69 or is it closer to 71? Well, it's actually closer to 69 than it is to 71, but not by much. So we'd expect 69 abundance to be slightly higher than the 71. With these isotopes, we need to recognize that the masses we're seeing are dealing with the fact that they have different isotopes that exist in nature, and those isotopes have different natural abundances. You need to be able to do the calculations where you calculate an average mass given a percent abundance. You then need to be able to calculate the percent abundance of each isotope given all the masses. Okay, so continuing on with our discussion of the atom and moving on to something a little bit easier but still equally important is dealing with formation of ions. All right, you need to recognize this name, cation. Cation is going to be an atom or a molecule that's going to lose electrons. If we lose electrons, it's going to become positively charged. Why? Well, because electrons have a negative charge. When we pull them away, we get excess positive. So let's look at a sodium atom. Sodium atom has 11 protons and it has 11 electrons. A neutral sodium atom does. If we take one of those electrons away, we now have 11 protons, 10 electrons. Well, a plus 11 plus a negative 10 gives me an overall plus 1. The fact that I have a plus 1 charge means that I'm dealing with a cation. Notice though, the number of protons did not change. The number of protons defines what the element is. The number of electrons is going to define what its charge is. So the other side is something called an anion. That's when an atom or a molecule gains electrons. If you gain extra electrons, you're going to become negatively charged. So let's look at a chlorine atom. A neutral chlorine atom should have 17 protons, 17 electrons. If we add an additional electron, now we have 17 protons, 18 electrons. Well, a plus 17 plus a negative 18 will give me an overall value of negative 1. So I would write Cl negative. That is an anion. So cation loses electrons, becomes positively charged. Anion gains electrons, becomes negatively charged. It's the number of electrons that are changing, not the number of protons. Some important facts you should remember. When we're dealing with chemical reactions are going to be dictated primarily by the electrons. And as we progress further and further into the course, we'll be talking more and more about that. A very important thing though, remember, I know I've kept saying it over and over again, but it's so important. All atoms containing the same number of protons are called by the same name. The number of protons defines what the element is. And we can't change the number of protons. If we change the number of protons, we change what element we're dealing with. And those are going to be nuclear reactions. Now, atoms of the same element can have different number of neutrons. That'll cause different isotopes of that same element. And if atoms have an equal number of protons and electrons, they're going to have no net electrical charge. They're going to have an overall charge of 0. But if we add electrons, we form anions. It becomes a negatively charged. If we subtract electrons, it becomes a cation. It becomes positively charged. So when looking at the slide, you may want to pause the video. It's good practice for you, and then you can just check your answers as I go through it. So you need to either fill in the atomic symbol, or you need to fill in the number of protons, number of neutrons, number of electrons. So first one, number of protons is 14, number of neutrons is 14, number of electrons is 14. First thing we need to do is we need to figure out what element are we dealing with. Well, what defines what element we have? That's the number of protons. So what element has 14 protons? Pull out your periodic table, you'll see that it's silicon. So we know number of protons then, we write in the lower left. It's the atomic number. Now we need to write something in the upper left. What goes in the upper left? Well, that's the atomic mass. How do we get the atomic mass? Well, that's the number of protons plus the number of neutrons. In this case, 14 plus 14 would be 28. And then we'll want to worry about the upper right, which is where our charge will go. So in order to determine charge, we need to look at the number of protons and the number of electrons. Okay, so we have 14 protons, that's a plus 14. We have 14 electrons, that's a negative 14. So 14 plus a negative 14 gives us an overall charge of 0. Now we don't write 0 up in the upper right. Because it has no charge, we just leave it blank. So that would be our symbol for that particular one. All right, let's look at the next one. How many protons do we have? Well, we'd have 6. Okay, first off, it's carbon. Second of all, the lower left tells us we have 6. How many neutrons do we have? Well, we have a mass of 12. We have 6 protons. So 12 minus 6 means we have 6 neutrons. How many electrons do we have then? Well, there's no charge. So if we have no charge, then the number of protons has to equal the number of electrons. So we'd have 6 electrons. All right, let's move on to the next one where we have ruthenium. How many protons? Be 44. How many neutrons? Be 57. 101 minus the 44. How many electrons then? Well, we have a plus 2 charge. In order to get to a positive value, we have to lose electrons. So we'd have 42 electrons. We could look at it as a plus 44 plus a negative 42 gives us an overall plus 2 charge. All right, so last one. We have 53 protons. Tells us it's iodine. So we can write a 53 in the lower left. We have 74 neutrons. So 53 plus 74 gives us our 127. That's the overall mass. We have 53 protons, so a plus 53, 54 electrons, so a minus 54. So positive 53 plus a negative 54 will give us a negative 1 charge. So given the number of protons, neutrons, electrons, you should be able to write out the atomic symbol. Given the atomic symbol, you should be able to write out the number of protons, neutrons, and electrons. Last thing I want to mention is I want to talk about molecules and chemical formulas a little bit. So molecules are going to be things that are going to combine more than one atom of an element. And it could be more than one element as well. So in order to visualize what's involved in a molecule, we need a chemical formula. Chemical formula is going to tell us which atoms are found in the molecule, and it's going to tell us what proportion they're found in. So let's look at some examples here. If we look at water, it's H subscript 2 O, H2O. Means we have 2 hydrogen atoms and 1 oxygen atom. We have carbon dioxide, CO2. Means we have 1 carbon, 2 oxygens. Carbon monoxide, CO, 1 carbon, 1 oxygen. If you look at H2O2, the hydrogen peroxide, we've got 2 hydrogens and 2 oxygen atoms in a hydrogen peroxide molecule. Okay, so those chemical formulas tell us what's actually in the molecule, and that's going to be important. Another thing that's going to be important is identifying what we call molecular compounds, sometimes called covalent compounds. Molecular compounds are going to be formed from nonmetals. We then are going to have to worry about something called ionic compounds. Ionic compounds are going to be formed from a metal and a nonmetal. Okay, so start thinking about those. Those are going to be important when we get to naming. All right, and last thing here is picturing these molecules. You're going to see different representations of the molecules besides the chemical formula. So picturing these molecules, you're going to run across some different types. We need some way of visualizing these molecules because molecules actually occupy 3-dimensional space. When you write a chemical formula, it doesn't tell us anything about the 3-dimensional space that this molecule occupies, what its structure is. Right? So a lot of times we'll have different ways of showing these molecules. Problem is we want to represent molecules in 3-dimensional space, but most of the time we can only represent them in 2 dimensions. In other words, putting them on paper or putting them in a PowerPoint slide, right? So we need some way of picturing those, right? So we can write something called a structural formula, which shows how atoms are connected to each other. We could do a perspective drawing, shows how atoms are connected to each other, but gives it a little bit more 3D shape. That little black wedge represents that hydrogen as if it was coming out towards you. That hydrogen with the dots represents going back away from you. Right? And you can see it kind of gives you a little bit more of a 3D view of what that molecule would look like. And then the fancier ones, we can have the ball and stick model. You can definitely see a little bit more of a 3D picture from that. and something called the space filling model. Right? All of those are ways of picturing molecules on 2D space. And so whenever you're trying to think about molecules, you can start thinking in terms of what these structures would look like. And eventually at the end of the course, or towards the end of the course, we're going to get into the perspective drawing side of things to represent these molecules. All right, so we've talked about the atom, we've talked about molecules, we've talked about a lot of things. And that brings us to the end of our discussion on the atom.